Okay, welcome back, ladies and gentlemen. In this video, we're going to be looking at inelastic collisions. Of course, I got the title here. So first, let's get to a definition. Now, it is a collision. We're talking about collisions between two objects, but by definition, an inelastic collision is one in which the total momentum of the system is conserved, but the total kinetic energy is not. So think about this for just a moment. The momentum is conserved. In order for that to be the case, of course, the net force acting on the system must be zero. But when this occurs, the kinetic energy is not conserved. We see a loss of energy, or possibly, in certain circumstances, a gain of kinetic energy. But most of the time, we're going to be looking at situations where it's going to be a loss, a decrease of the kinetic energy of the system. So under this definition, we see that, well, the change in momentum will be zero. In other words, the final momentum of the system will be equal to the initial momentum of the system. We see a change in kinetic energy of the system that is not zero. In other words, the final kinetic energy of the system does not equal the initial kinetic energy of the system. So we've got the definition in words, we've got it in symbols. Now for a truly, completely inelastic collision, we see the objects collide and stick together. For a truly, completely inelastic collision. And this is somewhat common. In fact, the opposite of an inelastic collision would, of course, be an elastic collision. And a pure elastic collision, really, you simply might think of it as darn near impossible. Just about every collision is at least partially inelastic to some degree. Some of them are very inelastic, and in this case you can get sort of a maximum, I guess you might say a maximum position in that category, so to speak, where the two objects collide and stick together, and you end up with one object instead of two. You see this in examples where, for example, the cars on train tracks will collide, and hopefully the collision is gentle enough, but they bump into each other and they hook together, and instead of two separate objects rolling on the track, you now have one object rolling as a single piece. Now, these two bits about momentum, the final and the initial, we can look at each one of those sort of independently. We know that the initial momentum of a system is equal to the momentum of object 1, or if we're going to have two objects, we'll have momentum of object 1, which is m1v1, and that is an initial velocity. And we're going to have to add the momentum of object 2, m2v2, initial. And we also know that final final momentum. And now in this case, the objects have combined into one. So what we have is m1 plus m2 when they collide and stick together. And since they are now one object, they have one velocity. and that is the final velocity of the system. And there's an interesting consequence of this. We know that initial momentum is equal to final momentum. Then we get this equation that comes about. We can see that m1 v1 initial plus m2 v2 initial. So in other words, I have the total initial combined momentum of the system. That's going to be equal to the total final combined momentum of the system. M1 plus M2 times the final velocity of the combined objects. Now this is handy in that it's going to be sort of convenient for us to rearrange this equation and isolate the final velocity of the system. And that is exactly what we're going to do. So check this out. Kind of put this in view so I can look at this and rearrange it. I'm going to solve this equation for final velocity, and I will have m1 v1 initial plus m2 v2 initial, and I'm going to have to divide by m1 plus m2, right? Okay. Now, here's something you want to know. This is a very general relationship. This is going to apply to all inelastic collisions where the two objects stick together, to those that are truly completely inelastic. And that's important, that only when the two masses combine into one does this apply. There are one or two special circumstances where this simplifies a bit and becomes something handy and easy to use. So, some special cases. First special case I'm going to look at is if the masses of the two objects are the same. In other words, if m1 equals m2, right? Then we see this equation simplify quite a bit. We're going to have our final velocity equal to mass times velocity of object 1 initial plus velocity of object 2 initial, and divided by 2m. So we can further simplify, of course. The masses cancel out, right? And we see 1/2. I got the 2 in the denominator, 1/2, multiplied by the sum of those initial velocities. Well, look at what's going on here. I'm adding two velocities and dividing by 2. In other words, I'm finding the average of those two velocities. So essentially, I have the final velocity of the system being equal to the average velocity of the two initial velocities. The average of the two initial velocities, I should say. So that's kind of I should say initial. Sorry, there we go. Average initial velocity is what you're going to get for the final velocity. All right, fair enough. Now, though, the other special case. This was one special case here, where the masses were the same. The other special case comes about where one of the objects is going to be motionless. And you know what, we'll keep this condition. And the masses are equal. So we started just with looking at equal masses, and now we're looking at one of them is motionless along with equal masses. And when we combine these two conditions, we're going to see that the final velocity comes out to m times the velocity of object 1. Remember, because one of the objects has no initial velocity, it would be 0. So object 2 in this case would have 0 initial velocity, and I'm going to divide by 2 times m, and of course mass cancels, and what we have is 1/2 the initial velocity of object 1. So when one of them is stationary initially and the two objects have the same mass, then after combining, the final velocity of the combined object is going to be equal to 1/2 of the initial velocity of the first object. So it's almost like during the combination you doubled the mass and you got half the velocity, and that's to allow for the momentum to be conserved. So some interesting things, these special cases. I will put some boxes around these guys. They are not universally useful. They are, by special case, we mean they only apply when the circumstances are such that they work. But when those circumstances exist, these equations are much simpler to use, right? Okay. What I'd like to do next is work through an example of a problem dealing with an inelastic collision for you, and I'd like you to see in this problem that we can verify that momentum is conserved, or work with, that's what I should say. I should say we will work with the conservation of momentum to find a final velocity. And we're also going to look at the kinetic energy of this of the system in this example problem. And we will, by looking at the kinetic energy before and after the collision, we will demonstrate that kinetic energy is not conserved. So here we go in this example. This example comes from page 291. This is question number 32, just for reference. And in this question, we're given that there's a block of wood, and so I'm just going to do a block of wood kind of drawing here. And we're told that the block of wood is resting on a frictionless surface. That's kind of nice. And there's a bullet fired at the block of wood. So, bullet fired at the block of wood. The bullet will pass through the block of wood. And so here's our general kind of scenario. Now, there's some specific information we are given. There is an for the bullet, lowercase b for bullet, and capital B for block of wood. Initial velocity of the bullet we are given as 650 meters per second. We're given the mass of the bullet to be quite small, only 4 grams, so 0.004 kilograms. We are given the initial velocity of the block to be 0. It's at rest. We're given the mass of the block to be 95 grams, or 0.095 kilograms. And after the bullet has passed through that block of wood, we are given, we are not given, I'm sorry, there will be a final velocity, but we do not know what it is. We're not given that velocity. In fact, that is going to be what we're looking for. There's one more bit of information that will be important. We need to know, after the bullet has passed through the block, what happens to the block. It turns out that the block will have a final velocity of 23 meters per second along the frictionless surface. Call that direction. So we have a positive direction to the right, positive direction to the right. We're being consistent. Okay. So here are, I'm going to outline the 3 questions that we're actually looking for. Part A, we are going to find, I missed a symbol here, didn't I? Final velocity of the bullet. We're going to find the bullet's final velocity. Part B, we are asked essentially what happens to kinetic energy of the system during this collision, right? Part C, we are asked to calculate the initial and final. Calculate the initial and final kinetic energies of the system. And we can handle this stuff. So here we go. I'm going to give myself some more space. I'm going to keep this one nice and clean so we can refer to it if we need to. Part A. Looking for the bullet's final velocity, right? Well, momentum will be conserved in this collision. The net force acting on the whole system will be 0. So if momentum is conserved, the initial momentum of the system will equal the final momentum of the system. And so how do I break this up? Well, initially, the bullet has momentum. It is moving, but the block does not. How would I find the bullet's momentum? I would simply say mass of the bullet times the bullet's initial velocity. And also, part of the initial momentum is the initial momentum of the block. Mass of the block times the block's initial velocity. And these 2 terms combined are the initial momentum of our system. It's going to be very nice that this goes to 0 because initially the block of wood is not moving. How about the final momentum of our system? Let's look at both of these. There are 2 terms here. We have a mass of the bullet times a final velocity of the bullet. And we have a mass of the block times a final velocity of that block. Neither of these 2 terms goes to 0 because after the collision, the bullet is still moving, and we're asked to find its velocity. And, well, I guess I should say we assume it's still moving. Possibly we get an answer that is 0, but it's unlikely. And we know the block is moving, so we have to just do some rearranging and then some substitution here. Rearranging because the answer that I'm looking for is that guy right there. That's my goal. So I will subtract this term from both sides, and then I will divide by the mass of the bullet. So I'm looking for the bullet's final velocity. I'm going to subtract mass this term from both sides. So I have this momentum, which is mass of bullet times bullet's initial velocity. I'm going to subtract mass of block times the block's final velocity. I'm going to divide by the mass of the bullet. Quick substitution, and I should be able to solve. And initially, my answer is 103.75 meters per second. For you people with figures of significance, that gets you 1.0 times 10 to the 2 meters per second. There is our answer. So I just looked at all these individual terms and found all those numbers from our initial information here. Mass of the bullet, mass of the block, initial velocity of the bullet, final velocity of the block. Here's my unknown in that problem. Okay, seemed pretty straightforward. Part B Now, remember, for part B, I'm now looking for what happens to kinetic energy of the system during this collision. Well, imagine this. In order for the bullet to force its way through the block, it's got to deform the block. In the process, the bullet itself probably gets deformed, so we have work being done on the block and work being done on the bullet. The bullet is actually passing through and rubbing against the wood fibers in the block at quite a rapid speed. There will be lots of friction. It's for a very brief period of time, but a lot of friction, and so there will be some heat generated as well. So a quick statement, some kinetic energy is lost to heat and work done on the block and on the bullet. Now, we haven't studied heat or thermal energy, but essentially it is a legitimate form of energy, and if you're creating heat, then there has to be some source of that energy. Thermal energy is measured in joules, heat is measured in joules quite often as well. And so work energy theorem, it's a form of energy, kinetic energy is form, work is equivalent to energy. There you go. Now the final task that we have is to calculate the initial and final kinetic energies of the system. So that should not be terribly difficult. So part C. Let's find the initial kinetic energy. Well, the equation is very straightforward, 1/2 mv squared. What mass will we use? Well, let's look at this. I mean, we have two objects. Let's break this down into bullet, velocity of the bullet initially, and that individual term is squared, right? 1/2 mv squared. But we also have the block. 1/2 mass of the block times initial velocity of the block squared. The nice convenient thing here is that initially the block has no kinetic energy, so this whole term goes away. And a quick substitution here for these other two terms is going to yield the mass of the bullet times the initial velocity of the bullet. And that term is squared. Please do not lose track of your exponents. Please, please, please. And you do this calculation, you get the initial kinetic energy of your system coming out to 845 joules, and figures of significance we get 850 joules. Okay. Now we need to calculate the final kinetic energy of the system. I'm going to set it up the exact same way, and it's smart to do that. It was convenient that this term went away to 0, but for the final condition, remember, both the bullet and the block are moving, so they both have kinetic energy. I can't get lazy. I have to keep this stuff in mind. So 1/2 mass of the bullet, final velocity of the bullet squared, plus 1/2 mass of the block times final velocity of the block squared. Do that substitution. 0.004, and this is a final velocity of the bullet, which I got to be well, this is 100 meters per second. I'm actually going to use a number with less rounding in it than this one. I'll use, let's go with 104. So that will introduce less rounding error into my answer. I don't know if that's going to make a big difference or not, but nothing wrong with doing that, with trying to incorporate less error as you go. And now, okay, so mass of the block, we've got 0.195 kilograms, and final velocity of the block was 23 meters per second. I've got to remember to square that. Easy peasy lemon squeezy, we come out to 46.8 joules. And again, if you're nitpicky about sig figs, you really want to say it's just 47 joules. There's your final kinetic energy of the system. Look how much kinetic energy is lost here. There's quite a bit of kinetic energy lost, and yet momentum was still conserved. All right, so look at what we did. Quick recap. Bullet fired at the block, stationary at first. The bullet slowed down, the block picked up speed. When we consider the entire system, momentum was conserved. But despite momentum being conserved, during this collision, we demonstrated that a significant amount of kinetic energy is lost. And it goes into, primarily goes into doing work, deforming the block and the bullet, right? Very similar to doing work on the crumple zones of a car in a car crash. And the idea there is to absorb that kinetic energy of the car and the occupants to slow them down and reduce that kinetic energy in a safer way by actually destroying the car and having work done on the car. And hopefully not much work done on the occupants. That's the idea there. Thank you for watching. I will see you next time.